Okay, let's get right into it. Welcome to this explainer, where we're going to completely unpack the ultimate strategy for mastering Cambridge Mathematics 9709. Today, we're cracking open the examiner's actual playbook. We're zeroing in on one of the most absolutely crucial, yet honestly easily fumbled topics in the entire syllabus: differentiation, and specifically, stationary points. Look, if you know the math but you're still somehow bleeding marks on the exam, this one is for sure for you. Let's get started.
The stakes here, well, they're incredibly high. Check out this quote straight from a senior examiner. They said that the difference between a B and an A star often comes down to how well you handle differentiation and stationary points. Think about that for a second. It's not just about, finding a derivative. It's about precision, it's about logic, and it's about showing the examiner exactly what they want to see when they want to see it.
So, here's our playbook for today. We've got 5 key areas to tackle to secure those vital method marks: core principles, technical methodology, critical analysis, examiner warnings, and we'll wrap up with exam strategy. All right, Section 1, Core Principles. Let's build the foundation of our entire methodology.
So the assessment framework basically targets 3 distinct cognitive domains, kind of like slices of a pie. The first slice is knowledge and understanding. That's just knowing your basic formulas. The second is application, which is actually using that formula. But here's the secret. That final slice, analysis, is the ultimate decider for top marks. This means you have to be able to interpret what a stationary point actually represents in the real world of the problem.
Now, what's super interesting about this is the clear contrast in strategy. Examiners heavily reward analytical depth, not superficial breadth. Superficial breadth is kind of just throwing every derivative rule at the page and hoping something sticks, but analytical depth, that's your A-star strategy right there. It requires logical reasoning. Principal examiners actually point out that making cross-topic connections, like linking stationary points back to coordinate geometry, is what secures those significantly higher marks.
Moving on to Section 2, Technical Methodology. Because, honestly, knowing the theory is only half the battle.
We really have to ask ourselves, why do students find multi-stage analysis and grabbing those method marks so incredibly hard? Well, it's because differentiation problems are rarely just a single step. Most of the time, students aren't losing marks on basic arithmetic. They lose them because they fail to clearly demonstrate their chain of logic. Finding the derivative, setting it to 0, solving for x, and properly testing the point.
To make sure you capture every single mark, you need to execute this exact 5-step procedural framework every time. Step 1. Deconstruct the question. 2. Extract the relevant data. 3. Select your analytical framework, like choosing between the first or second derivative test. 4. Execute the math with crystal clear notation. And 5. Present your final answer using the correct terminology. It's like a guaranteed recipe for success.
And please remember this, your presentation and annotations are scrutinized just as heavily as the math itself. Seriously, you can't just leave a floating x equals 2 in the middle of a blank page. Examiners expect to see proper headings, the right terminology like specifically stating maximum or minimum, appropriate formats, and clear tracking of your entire thought process.
Let's jump into Section 3, Critical Analysis. This is where we look at the specific, evaluative thinking that separates the A-stars from the Bs. To hit those top scores, you've got to actively evaluate your evidence. Don't just blindly apply the rules like a robot. Top candidates identify limitations. For example, they'll ask themselves, does my X value actually fall within the domain given in the question? They justify their decisions with hard proof, clearly showing that the second derivative is, say, greater than 0, rather than just randomly stating it's a minimum and moving on.
Also, when a question specifically asks you to compare the nature of 2 different stationary points, you really need to balance identifying both similarities and differences. And the trick here is to use clear comparative connectives to link your ideas while backing up every single claim with your actual derivative calculations as evidence.
All right, Section 4, Examiner Warnings. We are officially entering the danger zone.
Listen up, because this is a massive red flag straight from the principal examiner reports. The classic mistake is doing all that beautiful, complex calculus to find a stationary point, but then finishing it off with a totally generic, textbook-style conclusion. If your final answer doesn't directly relate back to the specific context of the question they asked, you are going to lose marks. No way around it.
If you want to stop bleeding those easily preventable marks, memorize these top 3 mistakes right now. Number 1, using the wrong mathematical approach for the specific context. Number 2, completely forgetting your presentation checks, which turns your working out into a disorganized mess. And number 3, like we just talked about, giving answers that are completely detached from the given scenario.
Now, under exam pressure, your brain can just freeze. It happens to the best of us. So to make sure you never miss a step, use a memory hack. Create a custom acronym for your core methodology, something that reminds you to check context, find the derivative, set it to 0, solve, and test the nature. Build a mental trigger that instantly snaps you back into the zone.
Finally, Section 5, Exam Strategy. Let's bring everything we've learned together into one foolproof system.
Here it is, your ultimate consolidated method mark strategy. Whenever you face a complex differentiation problem, follow this sequence. 1. Identify the key elements and the domain. 2. Apply the correct mathematical principles. 3. Execute your analysis with perfectly clear annotated working. 4. Verify your results. Does the nature of this point actually make sense for the function? And 5. Present your final answer clearly within the appropriate format. Which brings us to the most important question of the day. When you sit down for that exam, are you going to rely on generic, surface-level answers? Or are you going to apply this specific, examiner-approved methodology to absolutely secure your A-star? The only real difference between a good math student and a great exam performer is strategy. Thanks so much for hanging out for this explainer. Now go out, play the exam.